Ja, inte glömmer. Och klockan har slagit 9 så att jag vill välkomna allihopa till dagens session för utbildningsserien Accelerera och leverera som vi gör här på Medtech for Health. Och idag har vi två väldigt speciella talare tänkte jag säga. Inte speciella talare, men väldigt eminenta talare som ska få prata om någonting i mitt tycke och från min kunskap väldigt unikt. Vi ska nämligen gå in i någonting som kallas för MAXA Medtech. Så vi ska fokusera på hur man kan utnyttja svensk storskalig infrastruktur till max. Och idag har vi inga mindre än Ulla Elofsson och Söderberg från RISE. Välkomna!
Tack.
Tack.
Och jag vill jättegärna att ni också presenterar er, för ni är mycket bättre på er själva än vad jag är på er.
Ja,
Om er.
jag tror att vi gör det eller ska vi göra det precis i början här? Ja, det kan vi göra. Ja, god morgon allihop. Jag heter Ulla Elofsson och jag jobbar på RISE sedan många år tillbaka. Under den tiden så jobbade vi med ett projekt som hette MAXA Medtech. Och det handlar alltså om hur man kan utnyttja storskalig infrastruktur. Med mig idag har jag Söderberg, en kollega till mig, som ska ge lite djupare insikter. Jag tänker att han kan få presentera sig själv.
Yes, ja. Jag heter Kristoffer och jag har jobbat med synkrotrollmetoder sedan jag doktorerade ungefär. Lite innan till och med, så runt 2006 så började jag jobba med röntgenkristografi med synkrotroner. Och sen så gick jag vidare och jobbade med lågvinkelspridning eller SAX som vi kommer hänvisa till i den här presentationen, Small Angle X-ray Scattering. Jag har jobbat på MaxLab som det heter förr och MaxIV som det heter idag. Som beamline scientist säger vi. Och sen efter det så gick jag in på RISE och tog den kunskapen med mig för att hjälpa industrin att närma sig de här faciliteterna då, och förbättra sin forskning och bli spets inom sitt fält.
Ja, jag ska börja med att introducera lite det här projektet och varför vi gjorde det. Och sen kommer Kristoffer att ge lite exempel på hur man kan använda de här teknikerna. Just det är du som bläddrar, Kristoffer.
Precis.
Ja, vi börjar med en introduktion och lite bakgrund. Så det här projektet då, MAXA Medtech, det gjorde vi för ganska många år sedan, 2018-2019. Och anledningen till det var ju att MaxIV då ganska nyligen hade öppnat och man såg en vikt i att även medicinteknikindustrin fick tillgång till och började använda den här tekniken så man liksom kunde förstå lite mer vad det handlade om. Nu har vi också den andra, MaxIV, den jobbar ju med högintensiv röntgenstrålning, men ESS jobbar med neutroner. De här teknikerna gör ju, de här nya anläggningarna gör att man kan göra experiment som man tidigare inte kunde göra. Både vad det gäller tid, upplösning och känslighet. Och det och det här projektet då, det handlade om att man skulle sprida kunskap och öka medvetenheten om vad man kan göra med den här typen av tekniker och hur det kan användas inom medicintekniksektorn. Och inom projektet så kartlade vi vilka aktörer som finns på området. Och vi försökte se vad industrin har för intressen, och vi hade en workshop där vi tittade på synergier mellan olika företag och om det fanns gemensamma intressen som man kunde gå in och jobba ihop. Och sen se till att medicinteknikindustrin, eller att det fanns användning av den här tekniken och att den blev relevant för företagen. Så det vi började med inom projektet då, det var att försöka hitta strukturer. Medicinteknik är så oerhört brett. Så inom vilka områden skulle man kunna använda den här typen av tekniker? Och vi kom fram till att vi delade in användningarna inom 3 olika områden. Så att dels var det device och implantat och inom diagnostik. Och så försökte vi titta på vilken typ av användning man kunde ha av det. Och så inom device så tittar vi på materialkaraktärisering, man kan göra in situ-tester, man kan jobba med mikrobatterier till exempel. Och inom implantat så är det också materialkaraktärisering, och så kan man titta på ytan mellan implantat och gränsytan till vävnad då. Och man kan också mäta strukturen. Och man kan jobba med bionedbrytbara implantat. Man kan titta på utmattring och åldring i materialen. Och när det gäller diagnostik och biosensorer så kan man förstå kemiska, strukturella och cellulära förändringar vid gränssnittet. Och man kan validera verktyg. Och man kan till exempel jobba med magnetiska nano- och mikropartiklar för diagnostik och bärare. Så det finns många olika och såklart många fler användningsområden. Och Kristoffer kommer alltså ge lite exempel senare. Så den här kartläggningen då tittade vi på, om du kan ta fram en till, vilka aktörer som fanns som jobbade med den här typen av mätningar då, som var relevanta för medicinteknikindustrin. Och om du går vidare, och vi tittade på vilka företag som fanns, vilka institut, forskningscentrum, universitetsgrupper, alla möjliga typer av kartläggning av olika aspekter. Du kan gå vidare. En till, tack. Jag visste inte att det var det vi hittade var att det fanns ungefär 5 kluster där man var mer aktiv än inom andra områden, även om det fanns enskilda grupper eller forskare på andra ställen också. Nu kan jag gå vidare. Så, vilken nytta har du av MaxIV eller ESS inom medicinteknik? Och här lämnar jag över ordet till Kristoffer.
Okej. Så jag kommer byta till engelska. Det blir lite lättare med alla vetenskapliga ord som kanske dyker upp, som jag också ska såklart försöka förklara och hålla på en låg nivå. Men det blir svårt att presentera på svenska, tror jag. I switched to English, and I have a couple of case studies that I have prepared to showcase what you can do with these methods in different parts of medtech. I divided it into 3 sections. So we have inhalations and the lungs. So basically inhalers and the lungs. How like the plume looks and how it looks when it actually come down into the lung. And then we have bones and implants. We can actually map how the bone looks like, and we can look at, for example, the bone and implant interface and how how this is developing during maturation of this after the surgery. And finally, looking at polymer networks and microstructures in gels. So starting with inhalers and the lung. Actually, we first start with the inhalers. So in this first case study, Daniel Duke. So we have this here. We actually, if you want to go to the article, you have the DOI here. So Daniel Duke and coworkers, they were interested in measuring the actual concentration of a drug in a plume from an inhaler spray. And in typical measurements of an inhaler spray, you run into problems close to the nozzle. And this is because of very high, optical density. Basically, it's because the plume is so concentrated close to the nozzle. So if you have the nozzle here very close to the nozzle, you have a very dense spray. And this can make measuring very, very problematic, just because there's just so much there. For example, if you would do scattering, you would have backscattering events, and basically nothing would come through. And then the same thing happens with absorption or other types of measurements. So instead, they decided to use X-rays and tracer atoms. And in this case, they started to use X-ray fluorescence and the tracer atom bromine. And by using this, they can disregard the plume as a whole and simply just look at the drug. And in this case, the drug is simulated by the atom bromine. And then they could do this with the 1 millisecond time resolution, which means that they could basically take an image or a measurement every millisecond to see how this plume is developing and how the bromine is distributed within this plume during a time interval. And then they could actually do this with a 5 micrometer resolution or spatial resolution of the bromine atoms distribution within the plume. And just as a comparison, I thought it was interesting. So, I mean, it might be difficult to kind of relate to 5 micrometers. You can say that a very thin piece of hair is about 50 micrometers. So this is like a tenth of a very thin piece of hair, which is quite small. And this is their setup. And this is the entire setup. So basically, at the beamline, you have a incoming X-ray beam. Usually it's monochromatic, which means it's a single wavelength. It comes in and then it hits the sample here, which in this case would be the plume. And what they could also do is it's this whole setup here with the sample, with lasers, diodes and everything here in the chamber, it sits on a table. And this table can move around. So that's also how they can control where inside the plume they can measure. And this, I should say, is also very specialized, what we call sample environment. And this is the bread and butter of the beamline, basically. So it decides what you can and what you cannot do. So sometimes the beamline is not equipped with what it is you need. And then you can actually contact the beamlines, and they are more than happy to collaborate with you and develop whatever it is you need to measure whatever it is you need to measure. Because some of these techniques, especially when it's like this, is very specialized. What they also have here, which is going to be important later, is they have a laser. And with this laser, they can just measure what we call here the optical density. And that's basically just to measure how many particles are there in a way. So just to see how much light is blocked out. And this, they're going to relate them to the results. Oh, let's see. There we go. So they measured along the plume and across the plume by using the table to move everything around. And the results showed that the drug was actually homogeneously mixed in the plume over time, over the time span that they measured. And what you see here is in the blue curve, you see the laser light. This is basically measuring now how much of the plume is there at a particular time point. And then the red dots is the projected density of the bromine atom. And here you can see that the plume's density and the bromine density are following each other quite nicely. And this immediately just shows you that within the entire plume, we have a very nice homogeneous distribution of the bromine, which in this case would be the drug. So because they could also offset the sample relative to the X-ray beam, they could also probe differences in the edges relative to the center of the plume. And that's what you see in this bottom graph, you can see that as they go towards the center of the plume, they actually get more intensity. And this just shows that the plume is kind of like I don't know if you want to say like a cone shape. So we have more density, more drug, more propellant, everything in the center of the plume, and then it just trails off as you go to the edges, to the sides. And this could have implications on, for example, how the drug is distributed, how much actually reaches the lung, or if it starts to deposit itself in the mouth or in the throat area before it actually reaches the lungs. And this could be something that has to do with how the nozzle looks like and how you design this nozzle. And using this technique, then you can start to figure out how you're supposed to change this inhaler or maybe the propellants to get a more even distribution and maybe get more of the drug into the lung. So they could also see, so what they actually also did, and what I'm not showing here in any images, is that they also looked at different propellants because let's see if what you could see here. So they have this canister, and they could basically just put any type of propellant in here that they wanted to test. And they could see that there was basically not really much differences between them, but they could actually quantify them. And finally, they saw that what they measured actually matched what they could theoretically calculate. So this means that the method has a very nice accuracy. So you could, in a way, also theoretically calculate like how would the plume optimally look like, and this very much corresponded to what they saw. So it's a nice way to see that the method is actually working for them. So the pros and cons of this method. Basically, the most obvious one is probably that you need a tracer atom. This might be one of the problems with the method in a way. So you need something to trace in order to see inside the plume. You need something to be illuminating inside it that you can actually measure. But on the positive side, this is a non-invasive technique, and it works in high optical density that is very close to the nozzle, and that's important to realize that you can see everything. They actually even saw inside the nozzle, so they actually measured 5 millimeters inside the nozzle, and then up to 7 centimeters out. Yeah, so this could absolutely help with inhaler design, formulation, to improve dosage. And this could, of course, lead to, for example, less side effects, more efficiency. I should also say that even though these images look like it's a 3D kind of 3D results method, it's not a true 3D results. Basically, it's just slides. But you could, in a way, do a kind of like a tomographic representation by measuring at different angles and then putting this together. And then you can actually get a true 3D visualization. And I should say that this was published in 2016. And given that they already stated this in the article, it might actually be that they started to work with that, and that might even be possible today. So then we move on to what happens. We looked at, okay, so how does the drug distribute in the plume? And now we can actually go a deep dive into the lung and see how does the drug distribute inside the lung. So in this case, the researchers were looking at a rabbit lung to see how this inhaled drug could distribute in vivo. And what they did was they used synchrotron radiation computed tomography. I don't know if you heard the word CT, but that stands for computed tomography, like a standard method in many hospitals, I should say, although it's very expensive equipment. So this you can also do with a synchrotron. Now, in order to understand a drug's efficiency, then we must understand the regional deposition, which is affected then by various parameters. For example, the morphology, so the drug morphology, how the air is distributed within the lung. So that is how ventilated the lung is, and then how the air and the particles move, how they actually move inside the lung. So these are things that will absolutely affect how the drug will be distributed. Now, traditional methods have already probed these kind of questions. The problem is that you need different methods to solve these questions, which means that if you would do this at a patient, for example, you would need the patient to sit still through different types of measurements. And during each measurement, you need the patient to, you actually need the lung to be as much as possible in the same place so that you can accurately project the results from the different methods to each other. This can be a big problem actually. So what they wanted to do here is actually use synchrotron radiation CT and do everything with the same method instead. And this is also quite a quick method. So I should say that they do different measurements, but they only use the same method. So there's no changing time. They basically just probe everything. So what they used then, as I said, was CT, and we can call it even more. So it's synchrotron radiation K-edge subtraction CT. What this means is that they measure 2 times at different wavelengths. In this case, I think they used iodine, right? And so they measure basically before the optimal absorption edge of the iodine and then after. So the wavelengths that the iodine absorbs and doesn't absorb. And then they subtract. And using this, they could see like where is the iodine, or for example, they could inflate the lung or pump ventilate the lung with xenon gas, and then they could do the same thing, and then could actually see where the xenon gas is, and they can get an accurate picture of how and where the lung is ventilated. So this is a very strong method to use. So what they do, of course, they compare the normal lung to an asthma-induced lung. So these are the lungs in question, and they come from a rabbit under anesthesia. So it's actually a live animal, although it's under anesthesia. And what they could find was that the deposition was inhomogeneous, so didn't reach all over the lung, and they could definitely find what they called hotspots, and the hotspots localized in branches in this lung. And with asthma, this was aggravated. You could see that the hotspots are there, but they're less dense. And they could also see that the hotspots correlated with inflow. So basically, if you would flow for a longer time, the hotspots would just increase. But basically, the drug would stay at the same place. It would just become more concentrated. So what they say here is this explains that the hotspots in the branches where the particles can't follow the quick change in the flow direction. So when the air comes into this branch, it will naturally start to spread out, right? And this very quick change or turbulence that happens causes the particles from the drug to deposit itself where this branch is. This is what they found. And in the case of the asthma model, they could also see that the airway resistance was higher in the asthma lung, but it had a small change in the ventilation because if you remember, I told you that they actually used xenon gas to measure how the lung was ventilated. And it wasn't actually more or less ventilated in a way that was interesting, but it resulted in more turbulent zones instead. And this is why you have this change in deposition in the asthma-related lung. So the contrast used to get measurements that they used here was a routine iodine contrast that you get injected with at a hospital, for example. But at the beamline, you could use many other types of contrasts, of course, like silver, indium, barium. Basically, so like Ulla said, it's a synchrotron, right? So synchrotrons use X-rays, and X-rays scatter or interact with electrons. So the more electron dense the atom is, the more you can see it. That's the easiest way to explain it. So the pros with this technique is, of course, that they were able to capture everything in one measurement, circumventing these problems that the lung has to be positioned in the same way during a long session with various different methods, and then piece all of these results together. And it's also possible to follow kinetics by repeating these measurements. You can actually see, okay, what happens over time. And then I think the major problem here, specifically because it's an in vivo measurement, is that the radiation dose is quite high. So the thing with synchrotrons is that the X-rays are very intense. But for tissue and live tissue specifically, this is of course a big problem. For one measurement, they measured the dose and said that this was fine. But as soon as you had to do more measurements, it started to become problematic quite quickly. And another problem with this method might be that you need a contrast. This is maybe like a recurring theme when you look in this kind of way, is that you need some kind of a contrast. You need something to pop out. You need something to measure. But that's also the strength of the method, really, is that you can focus on something in order to make it visible in maybe what otherwise would be a complex mixture. Right. So we move on to bones and implants. So this is just a single slide. I couldn't really get hold of this article in its whole. But this is an article by Marianne Leby, who's actually working at MaxIV, at the NanoMax beamline. And here they developed a method to not only do some tomography on a bone, but also map how the fibrils in the bone actually align. So this is a very, very, very interesting, and at the time it was super new. It was a very, very cool method to see. And this is something that's otherwise very difficult to determine due to the nature of the fibers and how we can model them. So what they managed to do was first find the orientation of the cylinders, which is basically just, they just showed like, okay, so the angle of the cylinder, you see it here, is like it's tilted more or less, horizontal, vertical. But then what they also did was they basically dove into that voxel, as it's called, the volume pixel. And then they represented with a color how ordered this orientation is, so to speak. So this is visualized here. So you can have different levels of ordering within a fibril. So you could either you can have a very well ordered, so everything is aligned, or you can have something that looks like, okay, the overall order is like this, but in reality, the fibers aren't really all wanting to go the same way. So what they do, they basically just mapped this trabecular bone sample from a human, and then they went through every single voxel and mapped out how aligned everything was, and how yeah, they made a very, very interesting picture. So this can of course be used later if you want to see, for example, how breaks occur, and then you can relate this to how well ordered and aligned everything is in the bone. A very interesting method to use. And here they then combined small angular X-ray scattering and tomography to accomplish this. So the tomography, of course, just representing the image of the bone just outside, and then using SACs, they could just probe the microstructure of the bone. So moving on then to implants. We know since, I guess for a long time, that titanium implants have been the gold standard. A potential problem that I actually didn't know much about before. So my expertise lie within proteins, so basically solution structure in small angular X-ray scattering, right? So this is quite far from where what I usually work with. So very interesting to study this or to read about these things. But a problem actually is that sometimes you need surgery to remove this implant, and this could be, for example, because you get an allergic reaction or something like this, or in terms of kids, you need to remove the implant. So that's another surgery. And then when it comes to polymers, you come to a problem that they have a limited strength. They have a very long integration time, and there's actually a risk for degradation of the bone. So in this project, the authors wanted to look at the magnesium-based implant, which they found was biocompatible and as well as biodegradable. So meaning there was less problems, less risks of the body interacting negatively to the implant, and also it would degrade itself over time. And it also has the similar elasticity to the bone, which is actually quite nice as well. So specifically, they wanted to look at the bone implant interface and to see how corrosion affects the mechanical strength of everything. So what they needed to look was investigate the 3D structure of the implant and the bone during load. So basically, they put pressure on the system, and to see then when it breaks, how it broke, and is the interface a problem in this scenario? And this is something that conventional methods couldn't do. Instead, they turned then to synchrotron micro CT this time to visualize the implant at the same time, the corrosion layer and the bone structure. And then they simply just applied a load to see and follow the break as it occurred and propagated in the structure. So they actually reconstructed 3D volumes of this whole system, and then they basically just sliced it up, and then they could see within the bone in different sections, depending on how far into the bone they wanted to look, or how far they had to look to actually see these effects. So in their model, they used a rat bone, a rat femur, with a magnesium-based screw. And then they compared this, for example, to plastic implants and to titanium implants. So with the very high resolution that they could find with this method, they could see the strong outer layer of the bone, and they could also see the inner network of the bone. They could see the small cavities within the mineralized bone, and they could see the tubes in the outer region of the bone. So they had a very good view of the microstructure. And then after applying load, they could see fractures occurring within the implant as well as the bone, but not at the interface. And they then found that this points to a very strong integration between the implant and the bone. They could see corrosion layers as well, but they found that they didn't really compromise the initial stability. And compared to titanium and plastic, they could also see that the magnesium-based implants actually had a more tight integration in terms of bone bonding. So I could point here to where it's easier to see. So here we have the implant, and here we have the breaks. So this is a region before the break and a region after the break. And you can also see here, there's nothing actually on the interface, but in this case it's more close. And this is, I would say then more in the corrosion layer of everything. So with this method, it was possible to do an in situ 3D analysis under load, combining morphology and mechanics in one experiment. And with their high resolution, they could also visualize both the implant and the bone microstructure. And I don't know very much about this method, but one thing that is obvious is, of course, the radiation dose. That this could be a problem if you don't extract it and look at this ex vivo. So if you would, for example, investigate an animal or a patient, the radiation dose is again a problem when it comes to these methods. So moving on to polymer networks and microstructures in gels. So we start with an example where we start to, instead looking at how X-rays interact, we look at how neutrons are used. So we can use synchrotrons to generate, as I said, high-intensity X-rays, or we can use spallation sources like ESS, that's also here in Lund, just close to MaxIV, European spallation source, and then we can generate neutrons. There are other ways to do it, like in reactors, for example. I think in Grenoble, there is a reactor that also produces neutrons. The spallation sources, however, they can generate a more high intensity beam of neutrons. So you can actually do time-resolved experiments, for example, at the ESS that you really can't even approach at other sources around the world. So a typical example, just to show the uniqueness of the neutrons, is if you take a coffee pot. So you take the standard, like, iron coffee pot that you would maybe put on the stove, filled with coffee and water. If you would shine on this or beam on this with an X-ray beam, just a very intense X-ray beam, you would just see a blackness there would just basically be a shadow of the coffee pot on the detector. So you can't really penetrate the material because it's just so electron dense that the X-rays, they won't go through. If you would do this with neutrons, however, they will interact differently. So they don't interact with the electrons, they interact with the atoms. And not only that, they also interact with atoms differently. So differently with different atoms. There's probably a logic to it, but I don't know exactly that logic. But there is a very, very nice list of how the neutrons interact with various type of atoms. And in this case, it doesn't interact very much with these iron atoms. It would just shine through. And then it comes to the solution. And here it starts to interact quite highly with, for example, the hydrogens. And what you can then see is you can actually see, for example, if you put this on a boiler, you can actually see the water boiling inside this coffee pot rather than just seeing a black shadow. So you can actually see penetrate into materials that you otherwise could not do using neutrons. And if you look, for example, at softer materials, like in this case, a gel, we can instead see differences you can see different things with neutrons than we could with X-rays because the scattering signal will be different depending on what type of atoms we have in the material and how we handle it. So I will come to this a little bit more. But certain X-rays will scatter, certain atoms will scatter X-rays and neutrons differently. That's the take-home message here. And we can visualize the microstructure uniquely using the two methods separately. So they wanted to understand the hydrophobic surfaces of silicones. And the problem here is that they are prone to bacterial attachments, which would lead to biofilm formation and finally, hopefully not, but it's a problem that leads to hospital-acquired infections. So they investigate here how IPNs, which are interpenetrating polymer networks, how they can be used to relieve this issue. And IPNs are networks, just to explain it first scientifically, networks of interlaced materials. You could think of it like two fishing nets of maybe different meshes, for example, and then you intertwine these two meshes with each other, and then you have an IPN. That's the easiest way to explain it. And then they want to study two polymers, a hydrophilic gel and a hydrophobic silicon in this IPN network. So this system can be used as an efficient drug delivery system, but it can also provide effective antimicrobial surfaces, and this has already been shown to work. Now, the distribution of the polymers, however, is unknown, and they found that this could actually be important to understand how, the characteristics of this system. Why is it such a good drug delivery system and effective antimicrobial for surfaces, right? And then depending on how you make this, you get different effects. And to understand why you get these different effects, it's important to understand then how the distribution of these polymers are. So they used many different methods. One of them is atomic force microscopy. This really hasn't anything to do with synchrotrons, but they also use small angle X-ray scattering. They use small angle neutron scattering. And the method that I will talk about mostly here is spin echo small angle neutron scattering, a very specific type of method. So neutrons, as I said, they will provide a unique insight. And I try to visualize that here. So if you look at this whole system using small angle X-ray scattering, so you use X-rays, what you will find is that the silica, so the filler that they have, will dominate the signal altogether. So you will not see very much of anything else, but you will mostly just see the silica. If you move then to neutrons and you have the system in standard water, you would instead see that the hydrogel will have a low contrast compared to the silicon, but the same is also true for the silica. So everything is kind of like just a haze. So finally, if you then put this whole system in heavy water, so in deuterated water, you will then find the hydrogel will have a high contrast compared to the silicon, and we will be the most dominating signal in this whole system. So this is how you can then see how you can use these different methods to kind of show various microstructures within the material that you're looking at. So they used AFM just to probe the image, so to get an image basically of the surface of the IPN. And then they used spin echo sands to study the morphology of the bulk of this system. So here we can see the results, and what they found using atomic force microscopy, they found that the system had two distinct components. They could identify distinct domains, where one domain would be hydrophobic, and that would be the silicone, and another domain would be hydrophilic, and that would be the hydrogel. So you can see here, for example, the let's see here, amplitudes of hydrophilic areas and the hydrophobic areas, using just the AFM to start with, right? And then they use spin echo small angle neutron scattering. And here they could show that the hydrogel domains, they consisted actually of spherical subunits between 40 and 370 nanometer radius. And they also saw that there were long-range density fluctuations, as you would call them. So basically what you see here is you have a lot of these small domains or smaller domains. And then at longer distances, you could see that you have these density fluctuations. So these fluctuations are likely due to how these hydrophilic domains are distributed with rich and poor regions of this hydrogel. And in short, they basically found that the IPN is a hierarchical structure with hydrogel-rich and poor regions. And the implications of this is that this creates patches of hydrogel on the surface that are unfavorable for bacteria to attach to. And also, the regions of hydrogel inside the bulk will provide a route for drug molecules to diffuse to. So that's the short version of of everything. So it's a complicated method to use, and that's in a way also a con with this technique. It's complicated, and you don't really get an image unless you, of course, in this case, use AFM, but you will get correlation curves. And what you need to do is you need to model these correlation curves and interpret this data in order to get your results. So in this case here, you can see, for example, that these solid lines here are modeling, so the final modeling of the system, and they are made by combining these dashed lines and the dotted lines. The dashed lines would be then the compact hydrogel domains only, and the dotted lines would be the long range in homogeneities. So if you combine these, you get the final model, and this would then fit the data that they have. So the good thing here is that using spin echo sounds, they can get a very unique insight into the bulk structure with what you could see a huge length scale. So you could go from nanometers up to micrometers with the same method. So this is also, like I said, sounds is very good for complex materials. Simply because you can decide what you want to look at and what you don't want to look at due to the atoms themselves basically providing different contrasts for you. So finally, we're going to look at a small angle X-ray scattering study of what they call a responsive microgel. So basically, this can change redox state, for example. And when it does that, it will swell or deswell. And similarly, if you vary temperatures, this gel will also swell or deswell. So depending on what happens around it, this swell is going to react. So this can, of course, be used in different things like micropumps and biosensors. They can use methods like DLS, for example, to look at this microgel, but they will only be able to see the bulk properties. They'll basically just be able to see the size. You can't really probe into the microstructure and see what happens when the gel is expanding, when it's swelling and deswelling, what's happening with the microstructure of the gel. And SAX can, in this case, do both. So it can both see how big the bulk is, but then you can also dive inside the material and get what's called the correlation length, and basically see the average distance between cross-linking points inside the gel and see how they change as the gel swells or deswells. And then the question is, of course, how does this internal structure change with deswelling and swelling, and also with redox events? I could also say here that this little image here, is the essence of the SAX experiment. So you basically just have a sample, you shine X-rays on the sample, and then you get scattering, some kind of scattering event, which you capture on the detector, and then you model the results. That's true to any type of SAX experiment that you're going to do. If you're going to do it in solution, or if you're going to do it on like this type of material, or you can do it on paper, plastic, most things you can think of that the X-rays can penetrate and interact with. So using small angular laser scattering, they could extract the size, the shape, and the network density. But they could also see how these parameters changed with temperature, with redox state, and they could also extract the ordering of the system. And what they found was that the correlation length, so the crosslinks, the points between crosslinks, actually increased drastically near what's called the critical temperature. So this is the critical temperature is where things starts to happen. So if you have temperatures below the critical temperature, the gel will swell. And if you move above the critical temperature, the gel will deswell. Similarly, if you would have the gel in oxidized state, the gel will swell. And they explain this by the gel in an oxidized state would be more hydrophilic, so it will attract more water, right? And then if you would reduce it, you would have it relatively more hydrophobic, and then it will start to deswell instead. So what they found was that the correlation length in the swelled state was smaller than the deswelled state, as you can see in this image. So this is kind of what you could tell from the modeling and from the effects. So when you have the swelled state, you have a smaller correlation length. And it's important to realize here that you can't measure specific correlation lengths, but what you see in small angular laser scattering is the average correlation length of the entire system. So what they could see here was that the average correlation length was smaller than in the reduced state. You could see here that you have long distances between crosslinks here, even though you also have small ones, you have very, very long ones. And in this case, you have basically all of them are the same, but they are relatively smaller than the average state in the reduced or deswelled scenario. So what they also found was overall, the gel was more evenly hydrated with less separation into polymer-rich and water-rich zone, even when it was deswelled. And this they found because you can deep dive and do modeling with small angular scattering, or you could basically just look how the scattering curve looks like. So you could have that as a fingerprint, like if you do mass spectrometry, for example, you could look at, okay, what peaks are missing, for example. You could do the same thing here. So every scattering peak will result from different length scales in microstructure that contributes to the scattering event. And you can then immediately see that if you compare two materials, like in this case, you can compare the standard PNIPAM gel to this PNIPAM gel that is redox controlled. And then what you can see that the redox controlled gel actually missed one of the peaks that the PNIPAM gel had. And from this, they could immediately say that this gel was more evenly hydrated, because otherwise this peak is very it's there because you could see a specific type of length scale occurring because of these zones that otherwise appear within the material. So to summarize here, with small angular scattering, we can see into microstructures, and SACS can, just as spin echo SANS, it can cover a broad length scale, although it can't cover the as broad length scale as spin echo SANS. You can still see from small nanometers up to several hundred nanometers, even maybe up to 1 micrometer if you go to specific beamlines where you can put the detector very, very far from the sample. And we could follow how the structure changes the stimuli, like, for example, temperature or redox state. Of course, you can use any other type of stimuli that your particular system needs to change. You can use temperature, as I said, or you can use pressure. You can shine in a laser to affect the system and make something happen, and you can capture this event, what happens to the microstructure as things change, using small angular laser scattering. And as I said, also you can do this in solution or in a solid phase as well. The problem is that you need modeling, and sometimes the modeling can be very tricky. This is where you can turn to neutrons to make it less tricky, less complex. You can focus on one part of the system and model that instead. And then you can remove that part and model the other part and then put the two things together. And a big problem can also be sampler preparation. So it can be very sensitive to sampler preparation. You need to handle your material correctly, and you need to have a very good background subtraction in order to get an accurate measurement. So just like most other techniques that I showed, what you see here is the contrast between what you want to look at and the background that what you want to look at is in. And the better subtraction you can have of the background, the better is the signal that you can get from your system, and the more information you can get out of it as well. So that was a lot of information. So if you have any questions, of course, you can have them now if you want, or you can just email us later, and I think Ulla will talk more about this.
Glasklart. Jag lämnar ordet till dig, Ulla.
Ja, och nu kommer vi till vilken nytta man har som ett medicinteknikföretag eller någon som är i medicinteknikbranschen. Hur kan man veta att man har någon nytta av det här? Och hur får man tillgång? Ja, tillgång till det kan man få genom att söka finansiering i ett projekt till exempel. Om man lägger in i sin projektansökan att man behöver använda de här teknikerna, så kan man ju på det sättet få finansiering för det. För det är ju inte riktigt gratis att använda de här. Men man kan också söka stråltid på anläggningarna i deras öppna utlysningar. Så man vet vad man vill veta, och man har kunskap om hur man utvärderar resultaten. Som ni förstod så är det här ganska komplicerat. Så om man inte har expertkompetensen så är det kanske ingenting att satsa på. Och det är också så att om man söker den här typen av stråltid så behöver resultaten publiceras. För det kräver anläggningarna att man ska göra resultaten publika. Och det är ju inte alltid säkert att man vill det. Om man vill testa sina produkter på något vis eller förstå hur saker och ting fungerar. Just det. Och man kan också köpa stråltid på anläggningen. Det vill säga man betalar för den tid man utnyttjar. Men även då så behöver man ju veta vad man gör för någonting. Så om man inte är så hemma på det här så behöver man ju hjälp. Och då kan man ta kontakt till exempel med ett lokalt universitet eller ett institut. Eller det finns också företag som specialiserar sig på att hjälpa till med hur man alltså hjälpa till med ansökan eller köp av tid samt analyser. Man kan också använda RISE Simple X. Och det är ett nytt koncept som vi har. Just det. Tidigare så har Vinnova haft utlysningar för pilotprojekt för hur industrin kan använda neutron- och fotonbaserade tekniker. Men den senaste var för 2 år sedan tror jag. Och jag har inte hört direkt om det kommer en ny, men det kanske vi hoppas på att det ska göra det. För det här är ju ett jättebra sätt att testa om de här teknikerna ger någonting för den specifika problemställning, och också om man behöver ta fram en provuppställning som gör att man kan testa sina produkter till exempel. Det är ju inte säkert att man bara kan stoppa in dem i strålen, utan man kanske, som när man tittar på den här inhalatorplymen, då måste man ju ha en uppsättning som gör att man kan montera sin inhalator på ett sätt så att det funkar i strålvägen, eller man kan få det man vill mäta på i strålen precis. Så därför så kan det vara någonting som man också behöver göra, det vill säga ta fram en provuppställning om det inte finns. Så nästa slide. Så är Simple X då, det är någonting som RISE har på sin agenda just nu, eller som vi erbjuder. Och det handlar om att man kan samordna olika projekt eller företag för att använda, så att man samsas helt enkelt om stråltid till synkrotronbaserade tekniker då. Och det innebär att man kan få en snabbare väg, det vill säga och snabbare väg framåt till stråltiden, och det är enklare att få tillgång till de forskare och projektteam som vi har. Och det är också så att man behöver inte köpa, normalt sett när man köper stråltid på anläggningar så har de en minimitid så att säga som man köper in sig på, och det kan vara ganska dyrt. Så att det här innebär att man speciellt på ett tidigt stadium, eller om man inte behöver så mycket stråltid, kan dela de här blocken med stråltid med andra intressenter som är andra projekt eller företag som är intresserade av samma typ av strålförsök. Och det som vi har på RISE, om man nu inte vet om ens frågeställning kan lösas med den här teknikerna, så behöver man diskutera kanske med någon som vet mer, och det kan man ju kanske göra om man har tur på sitt lokala universitet där det finns någon som har överblick över teknikerna. Man kan också vända sig till RISE då. Vi har ett antal olika experter inom olika tekniker, så vi kan erbjuda liksom alla sorters mätningar i princip. Och vi har också en branschkunskap, så att om man vill diskutera om ens frågeställning eller ens problem kan lösas av att göra mätningar med de här teknikerna, så kan man komma och diskutera med oss. Så kanske vi kan slussa till rätt typ av mätning som man behöver göra. Ja, du kan gå vidare. Och det här var i princip allt som vi hade att säga idag. Men det går jättebra att kontakta oss i framtiden. Både jag och Kristoffer finns kvar på RISE, och där kan man alltså få tillgång till oss och våra kollegor.
Fantastiskt. Tack snälla Ulla och Kristoffer för en jättematnyttig session. Jag hör att ni är experter i området, och det är området som jag inte ens har hört talas om, ska jag säga er. Framförallt det du gick igenom, Kristoffer. Det här är inte första gången du gör det här, eller hur?
Både ja och nej kan jag säga. För den här detaljnivån kanske det på sätt och vis är första gången. Men precis, jag har ju sett och jobbat runt folk som har jobbat med de här teknikerna under många år. Så att, precis, det är både nytt och inte nytt. Det händer väldigt mycket.
Våra experter är ju oftast experter på en teknik och en typ av mätning. Men däremot så har vi då ett antal olika experter som har kompetens på olika tekniker. Men förståelsen generellt, det tror jag att de flesta av experterna har.
Absolut.
Bland annat Kristoffer.
Självklart, det tvekar jag inte en sekund på. Och Vi har ju en deltagare med oss idag kvar. Jag vet att du ska avvika alldeles strax. Jag såg din fråga i chatten. Men har du någon fråga till Kristoffer och Ulla innan du avviker? Eller är allting helt glasklart för dig?
Ja, det var långt ifrån glasklart. Det var lite här. Men jag hade en fråga. Som egentligen kanske var en sidofråga, men jag tänkte ställa den ändå. För det läste jag någonstans, och då fick jag en fråga här. Att om det var alltså inte vetenskapligt, alltså att man inte ska göra en studie men ändå ska publicera det, till exempel mer om det skulle vara för konst eller kulturarv. Då skulle det också finnas en möjlighet. Är det också erbjudande? Har ni koll på den biten?
Ja, det är lite svårt att uppfatta frågan. Kristoffer, har du något svar?
Jag har svårt att höra faktiskt.
Ja, precis.
Det var...
Jag skickar er frågan, för den var lite specifik. Ni får den på mejl.
Ja, okay.
Jättebra. Då kan vi komma tillbaka.
Tack snälla Kristina för att du var med oss idag. Då ska jag dela sista sliden så att vi får med det också. Tack snälla. Och det är kort och gott att jag vill välkomna till dessutom nästa session som är faktiskt bara nästa vecka. Och då kommer vi den 11 september klockan 9 till 10, en kort session den gången också, få prata om innovation i partnerskap för spjutspetsvården i region Västerbotten. Och jag välkomnar alla deltagare att följa med oss då och ställa era kloka frågor i vanlig ordning. Och med det sagt så vill jag än en gång tacka er två, Kristoffer och Ulla, för en jättebra presentation och för matnyttig information som jag är väldigt tacksam över att vi har spelat in så att fler också kan nå den här klokskapen som ni sitter på. För det behöver vi ute i medtech-världen. Tack snälla för idag och på återhörande.
Ja, tack så mycket.
Tack.